Hi guys, so today we're going to start our review of factoring, and we're going to start, as I mentioned yesterday, with learning how to factor out a GCF and factor the special case difference of squares. So everything on the front that you see here is factoring out a GCF, and on the back we'll move to difference of squares. Okay, again, we talked about yesterday a GCF is the greatest common factor. When we're looking for a GCF in a polynomial, that GCF, keep in mind that GCF could either be a number, a variable, or a combination of the two. Now, since factoring undoes distributing and FOILing, it works backwards. When we factor out GCF, once we identify the GCF, we're going to have to divide it out of all of our terms because that's the opposite, or that's what undoes distributing. Okay, so if I look down at that first example, I have three terms, 54x squared, 12x squared, or 12x, and 12. First thing I do is I look at the numbers, 54, 12, and 12. And I look to see what is the biggest number, if any, that goes into all these things. Okay, so I look at that, I see, and looking at those numbers, the biggest number that goes into all three of those terms would be a 6. So I write that number down. Now, variable-wise, in order for a variable to be included in the GCF, all of my terms have to have it. The first two terms have an x, the third term does not. So the only thing in my GCF here is a number, and that number would be 6. So I'm going to start with that 6. Now remember, I have to divide it out of each of these terms. So I end up with, on the inside, 9x squared plus 2x plus 2. And if I ever wanted to check this, I could distribute this back out, and I should end up with what I started. Okay, again, hopefully we remember this from Algebra 1. I told you yesterday this was going to be a quick refresh. So looking at number 2, very similar. Okay, I have 30x squared, 35x, and a 10. So I always look numerically first. The biggest number that 30, 35, and 10 have in common, that would be a 5. And then I check variables. In order to be part of the GCF, that variable has to appear in all the terms. Similar to number 1, I have an x in the first two terms, but not in the third. So my GCF is only the 5. I have to divide it out of all those terms. So on the inside, I end up with 6x squared plus 7x minus 2. Okay, moving on to the next one. Looking at those three terms, negative 12x to the third, negative 20x squared, and negative 4x. Numerically, they have a 4 in common. Now, just as a normally semantics thing, if our polynomial ever leaves with a negative, usually we will factor that negative out also. So coefficient-wise, I'm going to treat this as a negative 4. Variable-wise, this time they actually do all have an x. So when the variable is common to all the terms, I take the lowest occurrence of the variable. So I have an x to the third, an x squared, and an x by itself. So the lowest occurrence is just my x. So this GCF would be negative 4x. So again, I have to take that and divide it out of all three terms. So I end up with a positive 3x squared. Remember, when we're dividing variables, we're really subtracting their exponents. A positive 5x and a positive 1. Okay, so take a second, try number 4 and number 5. I don't think there's anything too different about those from the other ones. 6 is a little bit different. So take a second, pause the video, try 4 and 5. Okay, so hopefully we agree on 4 and 5. On number 4, the GCF was just 6x. And on number 5, the GCF was 5x. Now, number 6 looks different just because there's no numbers involved. That's okay. It's still an expression. I can still factor it. But I'm looking now for the GCF, and clearly, if it has a GCF, it's going to have variables. Now, it's possible sometimes that I will look at an expression and it won't have anything in common. There will be no GCF. So if I look at number 6, there are two terms, a to the 5th b, and just a by itself. So both terms actually have an a in common, and the lowest occurrence of a is just a by itself. So the GCF here is just an a. I have to take that a and divide it out of both of those terms. When I do that, I get a to the fourth b. Now, I'm sure some of you are thinking on that last term that those a's cancel each other out, and that's true. But whenever you take something with division and divide it by itself, it never cancels out to 0. It cancels out anything, whether it's a number or a variable or both. Anything divided by itself gives you 1. So when you talk about things canceling out when you're dividing, that's true, but it cancels out to have a 1 left. All right, let's look at those two on the bottom. Again, I think you can try these. So pause the video for a second, try these, and then check back. All right, let's see how we did. So 7 was a bit more complicated than 8. If I look at 7, it was only 2 terms, but those terms had lots of variables. So their GCF was 4. They both had an x. The lowest occurrence of x was just x by itself. They both had a y. The lowest occurrence of y was y squared. And they both had a z, and its lowest occurrence was just z. So their GCF was kind of large in comparison to some of the other ones that we did. But 8, the GCF was just 5x. Hopefully we are remembering this from Algebra 1 and we're smooth sailing right now. Okay, let's flip on the back. In Algebra 1, you also looked at some special cases. And one special case that you should have looked at was factoring a difference of squares. Okay, in order to factor a difference of squares, you have to meet 3 criteria. The first thing is that you are only allowed to have 2 terms. If you have more than 2 terms, you cannot apply differences of squares. The second thing is the word difference is fancy for subtraction. So if you do not have subtraction between the 2 terms, you also cannot apply difference of squares. Okay, and my third criteria, when it says difference of squares, I actually must have perfect squares. So everything involved within this problem must be perfect squares. So all of my variables and all of my numbers must be perfect squares. So let's talk a little bit about what that means. For a number, I'm thinking that most of you know your list of perfect squares. What I mean by that is 1, 4, 9, 16, 25, keep going forever. Now, if you would happen to run across a number that you didn't know if it was a perfect square or not. So let's say you ran into something and you weren't sure if it was a perfect square. Let's say I threw 289 out there. If you're not sure if a number is a perfect square, you type it into the calculator. And if its square root is a whole number, it happens to be a perfect square. If its square root is not a whole number, like if I threw 300 out there and you didn't know if 300 was a perfect square, type that in. 300 is not a perfect square. Okay, so when we're talking about what perfect squares are, I think most of the numbers will probably be pretty small and manageable, so you know whether they're perfect squares or not. But if you ever run into one that you're not sure, stick it in the calculator. If its square root is a whole number, that means it's a perfect square. If its square root is not a whole number, it is not. Now, in terms of variables, in order for a variable to be a perfect square, its exponent must be an even number. So things like x squared or y to the 6th or anything that's an even number, that makes that a perfect square. Okay, so let's say we meet all the criteria. So looking at number 1, I do meet all the criteria. I have 2 terms. I have subtraction. Both terms are a perfect square. When I meet the criteria, this difference of squares will factor into 2 binomials. That means 2 sets of parentheses. And you need to take the square root of each term. So the square root of x squared is just x. The square root of 36 is 6. Again, if you didn't know that, you can type it in the calculator. And then in between those sets of parentheses, one of them gets a plus sign, one of them gets a minus. And the order of that doesn't matter. The minus could come first and then the plus. So if I would FOIL this back out, I should end up with what I started. Now, we talk about checking our work all the time. I don't know if I would check every single problem, but if you FOIL this back out, you should end up to check it with what we started with, the x squared minus 36. Same thing in number 2. So I do my 3-part check real quick. I do, are there 2 terms? Yes. Is there subtraction? Yes. Are they both perfect squares? Yes, they are. So now I know this can factor into my two binomials. I need the square root of x squared, which is x. I need the square root of 64, which is 8. One's a plus and one's a minus. And I am usually in the habit of doing the plus first and then the minus. But as I mentioned, it really doesn't matter. So if you have minus first and then plus, as long as you have both the binomials, the order doesn't matter so much. Okay, so take a second, pause the video, try 3 and 4. All right, hopefully we agree. Again, we talked about this. I think one of my classes we got to talk about this a little bit yesterday. Hopefully this is something you remember from Algebra 1, like most of this factoring should be. Okay, now at the bottom, once we get rolling here on factoring, and we've talked about remembering all of our ways to factor, we will do a lot of layered factoring. What I mean by that is, it will be very rare for you guys being my honors kids that we will just do one kind of factoring and be done. A lot of times we might incorporate more than one factoring into one problem, and that's what these last two do. Okay, so when we factor, the first thing we always look for is a GCF. I don't care how big the problem is. I don't care how small the problem is. I don't care if we're factoring today or if we're factoring 2 months from now. The first thing we will always look for is a greatest common factor. If the expression has it, great. If it doesn't, okay, we move on to something else. So if I look at number 5, the first thing I look for is a greatest common factor. And I notice that those two terms do have something in common. They have a 2 in common. So my first step is going to be to factor that 2 out. When I do that, I'm left with 16x squared minus 25. All right, so after I factor out the GCF, then I need to look and see, is there anything else that can be done? So inside of those parentheses, if I examine this a little bit closer, this expression inside the parentheses meets my criteria of a difference of squares. It has 2 terms, there is subtraction, and everything involved in those terms are perfect squares. So I've got to bring that GCF, continue to bring it down with me, but then what's in those parentheses can further factor into 2 binomials. The square root of 16x squared is 4x. That goes in the front of each of those binomials. The square root of 25 is 5. That goes in the back of each binomial. One's a plus and one's a minus. So that's what that one looks like when it's fully factored. So take a second, pause the video, and try number 6. All right, so hopefully we agree. If I looked at number 6, first it had a GCF of 3. I factored that out. And then once again, what's left inside was a difference of squares, so I could keep factoring. And as we progress throughout this factoring, this will happen more and more. It will be very rare that we will just do one type of factoring and the problem will be done. It will be much more common that we will see layered factoring, sometimes even 3, 4 steps on this factoring. Okay, so the sub will have that worksheet for you guys. So finish that. I expect you to turn that in before you leave today. And then you have no additional homework over the weekend, and I will see you on Monday. Thanks.